Okay, so to situate us again, we've been building up this little model at an individual level of people's mortality and heart disease risk. Um, and increasingly, we've been supplementing it with mechanisms that look at summary data from this model um, that examine the emergent patterns that are induced by this model. This model with this open population with deaths and births coming into it, um, uh, that induces patterns and the prevalence of heart disease, and among those of different ages that are distinctive. There's a population pyramid or histogram that we've created, and we can look at those how the population as a whole and the population of certain subgroups varies. But there's many areas where we haven't really tapped the some of the greatest powers of agent-based modeling. In fact, many such areas. And we're trying to build up one step at a time. But I wanted to take one of those where we can add to this model potent risk factors, mechanistically established risk factors where causal pathways are understood biologically, physiologically, in terms of pathophysiology, in which bears a great deal on heart disease risk and indeed mortality risk. By so doing, it's not merely that we have a model that's more realistic, because we have to be cautious about that, in the same way that if someone told you your map of your city that you used for biking trails wasn't realistic enough because it didn't have stoplights and a superimposed map of the subway stations and of where crosswalks were, where where the railway tunnels were, etc. You would say, well, it's not needed for this map. There are cases where we want to be cautious about expanding it, but by having this impotent risk factor, which I'll show my hand, it's smoking, it's matters with tobacco use. We can actually expand our view to ask about the impacts on heart disease risk and burden of heart disease, and indeed burden of mortality that might ripple through from interventions related to smoking, preventive interventions. And another pattern that came out in your surveys of response for this event was interest in public health and prevention matters. And I thought that using a prevention lens here and a behavioral lens might be helpful and rewarding. So what we're going to do is we're going to supplement this model with a representation of smoking behavior. And we're going to see that it doesn't require a kind of combinatorial explosion of different possibilities. Even when we go to characterize the interaction between processes governing smoking and processes governing heart disease and mortality in turn. So we're going to turn our attention to a simple depiction of smoking, and one that will build on elements of what we've already induced, and will let us ask about those linkages, particularly from smoking to heart disease and by extension to mortality. Okay, so to do this, we're going to be adding in a different state chart. Okay. And this is going to be called smoking state chart. Could call it tobacco use state chart. I'm going to call it smoking state chart. And this is going to have 3 states. One is going to be called never smoker. You'll notice I tend to be deliberate in my naming, and I tend to name states with a capital, and I tend to name transitions with lowercase. And Jeff, I'm not forgetting the delfs. We'll deal with them in a little bit. Okay, so I'm gonna okay, so this thing needs to be centered. I want it to be kind of nicely centered. Okay, there we go. And what we're going to do is have a current smoker state, and we're going to have a former smoker state. And for each, I'm going to try to center the name and hope I won't have to expand these too large. A little bit needs adjustment. There we go. Okay. So you're going to help me reason about the transitions here. Someone's a never smoker. If someone's, let's suppose we posit, and it's a reasonable assumption, that people start as a never smoker. Where in this state chart could they go? Where does there need to be a transition out of never smoker to where does it need to travel? So if I consider a transition out of never smoker, where's the obvious place for it to go?
To current smoker.
Current smoker, indeed. It's not that someone's a never smoker and becomes instantly a former smoker. They do so by virtue of having smoked. So this is pretty clear. Now, we're going to pay attention to this transition in terms of our probabilities of having a chance per year of starting. But I'm going to note that it's a rate, and we'll come back and fill this in just a minute. And next, from current smoker, where might those transitions go? We're just putting the transitions in place, and then we'll fill in the details about the specific assumptions to be imposed. So we're adding the structure of the model. Remember, I said structure determines behavior. And we have some elements of structure already, and we're adding more elements of structure that will materially shape the behavior of the model as a whole and of individuals. So from current smoker, where else do transitions need to go? To where else?
To former, and vice versa can go back to be a current smoker, basically.
Exactly. And by the very name, you know that someone from a current smoker can't become a never smoker again. I mean, it's contrary to the very idea of a never smoker. So really from current smoker, they could go to former smoker. And we'll make that a rate again. Okay, so there's
Cantonese or Mandarin?
Okay, there's some sort of audio being picked up here.
Mandarin, right? Mandarin. Mandarin speed. Mandarin.
不是
Cantonese.
哎呦
I'm not sure what you mean.
Okay, so this audio is
I'm from Thailand.
okay, so I'm gonna
I
okay. Okay, thank you. Okay. So this one, we're going to make a rate transition. Oh, we should name these appropriately. This will be called initiation. I'm sorry. Initiation. This one will be called cessation. You could call it quitting if you want. I'm going to call it cessation. Sometimes you call initiation uptake. And this one we're going to call relapse. And this one will be a rate transition. Oh, come on, rate. Okay. Okay, so folks, we have these three transitions, but right now they're kind of untethered in terms of the rate assumptions. It's one per year, which, would be fearsomely high for children to become current smokers. So I'm going to go and we're going to give some parameters to impose for this. Later, we'll elaborate it with age-specific rates, but one step at a time. So we're going to go to main because these parameters will hold across the entire model, across all people. It won't vary on a per person basis. Therefore, it belongs, like birth rate, up here in the in main. Okay, so we're going to put in place a parameter called initiation rate. Hey, oh man, initiation rate. And its default value will be 0.1. We're going to put in place one called cessation rate. And its value is going to be 4.0. We'll talk about what that means in a moment. And we're going to put in place a relapse rate. Relapse rate. And its default value is going to be 6.0. We're going to talk what this means in just a second. But I'm going to go back to the state chart so we can see this. So we're going to hitch those up while the thoughts in our mind to each of these areas. So initiation rate is going to use the initiation, the rate of this transition will use the thing we call the initiation rate. How do I refer to that initiation rate? What do I need to put here to refer to that initiation rate? Can I just say initiation rate? If not, why not?
Should be main or population.
It's in Maine, exactly.
Yeah.
So it's up in Maine. So we have to do Maine.initiation rate. Okay. For current to former, instead of just saying cessation, we'll say Maine.cessation rate. And the final one for this, we'll say Maine.relapse rate. And I sort of built the model after each of those, but I was highly confident. So I deferred the build to the end. If I'd done it after each, I could have been spotted immediately. If I made a mistake in the first, it might be mirrored in the second, etc. But I took the liberty of putting it there, and I'm gonna yeah. Okay, so now we have these rates. Now let's talk about a rate. So I've told you before that the mean time within a state is a chance per unit time of leaving. So a chance per year in this case of leaving. It's a per year probability of leaving. Hazard rate, also called a temporal probability density for more STEM background. Okay, so if I have a hazard rate of leaving of A, my mean time in this state before leaving from that, if we don't have other things leaving it, will be 1 over A. the mean time is 1 over the rate. This is just a simple fact about Poisson distributions and associated with the exponential distribution. The exponential distribution, the amount of time I spend in this, the mean of it is 1 over the rate of leaving. So if I have a rate of an initiation rate of 0.1, I mean, on average, within 10 years, 1 over 0.1, I'm going to initiate smoking. I'm going to take up smoking. If I have a current smoker to former smoker, if I have a rate of 4.0 per year, you might say, well, that's not a probability. It's greater than 1. Yeah, it's not a probability. It's a probability per year. That's a different thing. It's a probability per year. And that means if its value is 4.0, the average time in the state will be 1 over that, or 0.25 years before I try quitting. Try because I go here. Again, if this is 4.0, my time in the state before leaving will be 1 over 4.0 or 0.25. If my rate here is 6.0 per year, that means I'll tend to spend 1 over 6.0 years here, or 2 months here on average, before I fall back into smoking on average. Now, if time allows, and this boot camp will make this a lot more elaborate, we'll have our chance of falling back into smoking depend on how long I've been quit. Something you can uniquely do at an individual level, you can't do at an aggregate level. So the longer I stay quit, if I've been quit for 1 day, my chance of relapsing in the next day is vastly larger than it is if I've been quit for 1 year and I want to consider my chance of relapsing in the next day. It's very much dependent on how long, partly because of the effects of nicotine dependence on the body, etc. We may elaborate that, but one step at a time. So we have this little state chart where we have these transitions between these states. Okay. Now, this is good, but I want to actually go and I'd like to have some visual representation of people's smoking status, if we could. So right now, these state charts are solitudes. This one doesn't affect the healthy heart, the heart disease state chart. And the heart disease state chart only affects the smoking one by virtue of mortality, right? Of people dying. That's a censoring event. Someone's not in a smoking status after that. But here, we'd like to be able to, first, before hitching them up, we want to be able to explore what's the dynamics associated with this. So we're going to do that. So you may remember we have this thing called heart disease color. Which denoted someone's status with respect to heart disease by the fill color of this oval, indicating their face upon the world. And now we have to somehow indicate their state, their heart disease status alongside their smoking status. And there's a couple of ways we could do that. We can make it their visual size. We can make it something about their shape. Make it something about their color. Put a little number next to it or something, or little indication. But I think what we'll do for simplicity, instead of making their fill color depend on, well, maybe we'll leave it heart disease color will be the fill color. We're going to make the boundary color depend on the smoking status. So just like we had declared this before, I'd like you to right click on it and copy. This is a common best practice or certain common practice. And it can be argued that it has salutary benefits. Right click on this. We have one color for one purpose. And we're going to have another one. From heart disease color, we'll call it smoking status color. And the reason I reused it is because it's already a color. It already has a default and will spare us a little bit of time. And here we're not just cloning it. I mean, we're using it for a different purpose. And actually, we're not going to be able to reuse that one. Smoking status color. Now, we want this to vary according to their smoking status. So, does anyone remember how we did that? Like, let's suppose we want never smokers to be lime green, something like that, to be green, kind of like we did here. How would we do that? Anyone? So we've added this new variable called smoking status color. We have this little state chart. And we want to have different colors imposed for this variable, smoking status color, depending on what state they're in. Suppose we wanted this state, that color to be set to green, and then we're going to use it in the oval for its boundary. How do we do that? What do we do? Well, when they enter here, just as we did here, we're going to set the color of that variable, of the smoking status, to be the appropriate one. So this is going to be smoking status color equals green. Do we need a semicolon? Are we computing something? Is this just a formula that computes a value? Or are we commanding it? Do it. Well, certainly doesn't qualify for a Greek chorus. So you tell me, come on, somebody tell me, do I need a semicolon or not?
Yes, you do.
We do. Okay. Current smoker. Thank you, Jeff. We're going to set that to be smoking status color equals red. Do we need a semicolon? Yes, we do. I'm telling it, do it. Former smoker. Oh, sorry. Smoking status color equals gray, I think. What is it? Gray? Is it? I always get it confused. Is it EY?
GRAY, I think.
Okay. Like gray poupon. I always forget which is. Okay. Okay. AY. Thank you. Thank you. Okay. Earl Grey is EY, I think. Yeah. Okay. Okay. So we've set this to 3 different values: green, red, and gray. And now we have to hitch this up here. We're going to set the line color to be calculated to be the smoking status color. Hey. And the line width, well, we want it to be big enough we can see it. That'll be pretty obvious. So we're going to use, mind you, we're overloading this. Like this is green and this is green. One's going to be a kind of ring around it. And the other will be the value in there. And I have mixed feelings about this, actually, because I'd like to sort of clearly communicate. But if both are green, we know, okay, this is person healthy in habits, healthy in outcomes. If the inner one is green, but the outer is red, we know, wait a minute, this person's habits are worrisome, but they're still fundamentally healthy at their core, in terms of their heart. Fittingly, the heart of the circle is the heart disease status. If it's red on the outside, red on the inside, we know, okay, this is a current smoker and they've done damage. If it's gray on the outside and red on the on the inside, we know, okay, well, this person had been a smoker. They probably contributed to that heart disease the risk of that heart disease. Okay, so build early, build often. And now let's run this model. Okay, so you help me parse here. Let's go look at a person here. So here's a person who's red in their core. The heart is red, but the outer part is gray. What does that mean about them? What's their heart disease status? Their heart disease status is the fill color. It's given by the fill color. So that's the thing internally. It's the heart of the circle. So what is that? Do they have heart disease or not? This red one.
Heart disease and is a former smoker.
It's a former smoker because it's around it. How about this person here? This here person. That's someone whose heart is
Healthy.
And their behavioral habits, their smoking status is
Never smoker.
never a smoker. Good.
I'm colorblind. That's still challenging for me to read.
Okay. Someone else should pitch in then. So how about this person here? This is
red means
red.
they're heart disease and a current smoker, I think.
They're a current smoker. That's right. Okay, so we're going to be looking at this, but right now there's no connection between the two, right? Like we shouldn't fool ourselves. Like right now we keep track of their smoking status, and if we continue running it, their smoking status should evolve. Yeah, people are their periphery is switching back and forth from current to former, for example. More and more of either current or former in the outer. But so it's evolving, but they're solitudes. They're like ships passing in the night. Smoking right now is not impacting heart disease risk. This heart disease risk is independent of their smoking status. Now, let me ask this. I mean, if we looked at older people compared to younger people, do you think that smoking, would there be an association coming out of the model, an association between smoking, occurrence of being a current, say, current or former smoker, an ever smoker, we'll call it, which is a common term? Is there a, if we looked at the model outcomes, would we expect to see some correlation between someone being an ever smoker versus someone having heart disease? Excuse me. Yes, between someone being an ever smoker and someone having heart disease, would we see that?
I think yes, because from what we've seen before, we are also expecting to be a difference because they were more time to be, the cumulative risk is higher, I guess.
Exactly. Exactly, Sarah. Excellent. So, we can actually do this. We don't need to just have it purely as a experiment in our heads, a thought experiment, a Gedanken experiment. We could actually calculate this. So let's go to our population. Let's suppose we wanted prevalence of heart disease among smokers, among ever smokers. No, among never, current, and former, to simplify our lives. Okay, so we could have this. You tell me prevalence of heart disease among never smokers. How would I make this statistic? What would I do? What sort of statistic would it be? It's a prevalence. Give you a hint.
I think
Sort
it's ever, because we want a fraction as well.
Yeah, exactly. And it's just the same thing. We're taking a prevalence. This is prevalence. What's the condition here? Who is to be counted in this?
Never smokers.
Never smokers. So how would we say the condition, the criteria, the stipulation is this has to be, I'll hint, an agent that is a never smoker. How would I do that?
Agent in state person dot never smoker.
Good. Agent dot in state person dot never smoker. Okay, how if I want to do this among current smokers? What do I do? Mutatis mutandis, the same thing, change some of the incidentals. Okay, change the basics. So I can do duplicate. Watch this. Okay, and I'll make this among not never smokers, but among current smokers. And what do I have to change here? What's the only difference here between this and this? What do I have to
Condition
change?
is
Yeah. Is what? Yeah, current smoker.
current smokers. Yeah.
Okay, next. Among former smokers. We'll do here former smoker. Let's make sure it builds. It's a happy camper. Okay. And now let's add it into our graph of the fraction with heart disease. How am I going to add that into our graph? What do I need to add to this graph? What do I need to do?
Add more and just replace the prevalence to be the one we are
exactly. Exactly. So, copy this. Okay. Fraction with heart disease amongst never smokers. And population dot prevalence of smoking among never smokers. There we go. Next. Among current smokers. And we will do the same thing, mutatis mutandis. Population dot prevalence among current smokers. Boom. And finally, it's just like chopping celery or something. It's just like, okay. Prevalence of heart disease among former smokers. Population dot prevalence of heart disease among former smokers. Okay. Now make sure it compiles. It's going to be a pretty big graph. Model's growing up. Okay. So let's go look. But I would posit that there's going to be some association induced by the fact that people who live longer have a higher chance of having started to smoke and have a higher chance of having gotten disease by their age. And we'll see this sort of play out here. You're starting to see some differences emerge here. So here, you notice there's a rather nice, rather pleasing way to focus in any of this. This is a fraction of the heart disease overall, the entire population. This is the fraction of heart disease among those 50 and up. This is the fraction of heart disease among those less than 50. Big difference here between this and this. We talked about that earlier. It's induced. That disparity is induced not by any sort of hard-coded difference, but by emergent results of the processes involved. Fraction of heart disease among never smokers, among current smokers, and among former. Very little between never and between current and former. They're really quite overlapped. But between never and current, striking. Even though I'm telling you, right now, there's no causal connection here between this state chart is not driving this one in any mechanistic way, in any causal way. But both, you're more likely over time to have reached, just as here as Sarah said, to have reached in current smoker or former smoker state over time. And that same time would have made it more likely you have heart disease. And so you have a quite striking difference between the rates among ever smokers, which are really quite overlapped, and never smokers. These ones are actually overlapped because people go back and forth so many times here. 4 times, 4 times a year on average that they come. I mean, in terms of they're likely to come here within a quarter of a year on average, and here 6, within 2 months, right? 3 months the other way, the 1/4 of a year. But yeah, so these two are so mixed that they're not materially different. But check it out: current never smokers, current smokers. So a certain amount of association here can be induced just by the underlying processes of risk, accumulated risk. And again, models help us think through the consequences. You might, at first glance, you might not have conceptualized it this way, that, okay, there's going to be large associations induced simply by these processes without any positing any causal connection that would emerge from this, and that we could explain a certain amount of difference simply with a very parsimonious model that posits the same risks on a per year basis, but greater induced risks, greater resulting risks over the life course. But we have confidence in this case, biologic confidence, physiologic confidence, and disease mechanism confidence. Sorry?
Sorry, I was going to say, shouldn't we expect also to see a higher fraction of people that are current smokers compared to former smokers, given that we have like the arrow to come back, kind of?
Yeah. So what you're saying is, what would the fraction? So is what you're asking, like, the fraction of people in the population that are current smokers or former smokers, never ever smokers? We kind of expect that over time to be higher and higher the later they are in life. Is that what you're saying? And eventually to out like a larger fraction will be ever compared to never over time? Is that what you're asking
I think
about?
that I would expect to be an assumption of the model, given that with more time, they would be also more likely to come back to current smokers.
Oh,
So
yeah.
maybe
Yeah.
that-
So, I see what you're saying. So I think I see what you're getting at. So this balance has to be, if they're here, they'll tend to rush here, they'll tend to leave here in just, a quarter of a year on average. Here, they'll tend to leave it in just 2 months, within 3 months here, a quarter of a year, within just 2 months here. So that will tend to induce more people being current smokers than former smokers. And that would stand to reason. Now so that would stand to reason. And we could actually test that, right? We could ask what fraction of the population. Well, gosh, let's do it. I mean, let's go to Maine, and maybe I'll distribute this version of the model first in case anyone would like it, and I'll stop this recording here, and then we'll go on and do that.